responds to the uncontrollable elements by observing and trying to understand them. Today, new techniques and a vast array of scientific skills extend man's knowledge of the forces that make the weather. Day after day, and all over the world, meteorologists challenge our inconstant air. From the dawn of his existence, man was in awe of the elements. He pondered the mystery of the clouds, the rain and the wind, and believed that supernatural forces control them. The Egyptians thought that the sun god, Ra, voyaged across the sky in a boat. Lightning, to the Greeks, carried the anger of Zeus. Storms at sea were the work of Neptune. American Indians worshipped a god of rain. And the Aztecs of Mexico tried to placate the god who controlled the winds. But in time, man's awe of the elements gave way to investigation. He devised instruments to observe and measure them. The thermometer was developed by Galileo in the 16th century. His pupil, Torricelli, invented the barometer, showing that air has weight and exerts pressure. Scientific pioneers investigated the behavior of the atmosphere. There were even adventuresome scholars who ascended into the atmosphere to study its composition. Benjamin Franklin was the first to express the idea that weather moves, that today's rainstorm in Philadelphia may wet Boston tomorrow. A few decades later in Germany, Professor Brandes documented the movement of weather. He painstakingly charted temperatures and air pressures for the leading cities of Europe. But Brandes could only diagnose the past. The data available to him were 40 years old. Today, weather reports from every part of the world can be obtained almost instantly. And Professor Brandes' techniques have become the basis of modern weather forecasting. Everywhere, every day, and generally several times a day, trained observers report on local conditions. They note wind and clouds, humidity, air pressure, temperature, and precipitation. The report from each station gives a comprehensive picture of local weather. Cooperation is international, for weather knows no boundaries. Today's weather at Vladivostok may move to Seattle next week. Because weather on Earth is affected by conditions above Earth, radiosonde balloons are launched into the atmosphere at stations throughout the world. The radiosonde is equipped to transmit measurements of temperature, humidity, and pressure up to a height of 20 miles. Twice a day, the radio signals report on conditions in that region of the atmosphere where most of our weather occurs. The speed and direction of winds aloft are computed by plotting the movements of the balloon. Out of an ever-growing mass of observations, meteorologists have evolved some understanding of what makes the weather. Our atmosphere is driven by vast amounts of energy, and the sun is the source of that energy. Only a minute fraction of the sun's radiation, about 1/2 billionth, reaches the Earth. And not all of this gets to the Earth's surface, because the atmosphere, with its gases, clouds, and dust, reflects and absorbs almost half of the radiation. Air is mostly nitrogen and oxygen, with a few other gases, including a small amount of carbon dioxide. Air also contains water vapor in varying amounts. Ultraviolet radiation from the sun reaches the atmosphere in potentially harmful quantities. But oxygen, high above the Earth, absorbs ultraviolet rays. Infrared radiation is absorbed mainly by carbon dioxide and water vapor in the lower atmosphere. However, visible radiation, or sunlight, streams through the air, and except where it is reflected by clouds, penetrates to the surface of the Earth. What happens to it then depends on the nature of the surface. Snow and ice reflect most of the light they receive, but land and water absorb light energy. They warm up and re-radiate energy in the form of infrared rays. Infrared radiation from the Earth, like that from the sun, is absorbed by water vapor and carbon dioxide, warming the atmosphere from below. This is called the greenhouse effect. The water vapor and carbon dioxide act like the glass of a greenhouse. Light passes through the glass. It is absorbed by the Earth, which heats up and radiates infrared energy. The air inside the greenhouse is warmed because the infrared energy is trapped by the glass. In effect, man lives inside a greenhouse created by the atmosphere. The sun also supplies the energy for circulating water vapor. Light energy is absorbed by the oceans and warms the surface water. Some of the water evaporates and becomes a gas, water vapor. Winds carry the water vapor away, often moving great quantities of it thousands of miles. The winds that blow across the United States transport about 6 times as much water as flows in all our rivers. As the moisture-laden air becomes saturated, the vapor condenses into tiny water droplets, and clouds form. Almost all the energy originally absorbed during evaporation is released as heat. This energy may affect local winds, thunderstorms, and hurricanes. Then, through a process which is not yet fully understood, clouds release their moisture as rain, snow, or hail. Water returns to the Earth's surface, and the cycle is completed. The chemical analysis of rainwater yields important new information. Chemists measure radioactive elements that rain has washed out of the atmosphere. This provides meteorologists with clues to the movement of air, the wind systems of the world. What makes the winds? What keeps the atmosphere in motion? Again, the answer is energy from the sun, and the fact that this energy is distributed unequally on Earth. In the tropics, more energy is received from the sun than is lost to space. At the poles, however, less energy is received than lost. A growing excess of energy in the tropics should make them hotter and hotter, while a growing deficit at the poles should make them colder and colder. But this does not happen. because the atmosphere transfers the excess energy from the tropics to the poles. Warm, light air at the tropics rises and flows toward the poles. Cold, dense air at the poles sinks and flows toward the equator. This would bring about a very simple wind system if the Earth did not rotate. The cool surface air at the North Pole would flow straight toward the equator. But of course, the Earth does rotate. The rotation deflects the winds, making them appear to blow along a curved path. The force that causes this deflection is called the Coriolis force. The cool surface air flowing away from the pole is deflected into a polar easterly wind, that is, a wind coming from the east. Some of the warm air that rises in the tropics and flows north cools and sinks. As it flows back toward the equator, it is deflected by the Coriolis force and becomes the belt of the northeast trades. Some of the air continues northward. It is deflected also and becomes the westerlies. The basic wind system of the northern hemisphere is mirrored in the southern hemisphere. And in both hemispheres, it is in the region of the westerlies that the greatest variability in weather occurs. The westerlies extend from the Earth's surface many miles up into the atmosphere and block the smooth transport of energy from the tropics to the poles. As a result, imbalances develop. The air on the equatorial side of the westerlies accumulates heat, while the air on the polar side is getting colder. This makes the region of the westerlies, where the bulk of the world's population lives, one of great meteorological stress. When the imbalances become too great, a mass of cold air breaks out of the polar region and pushes southward. And warm air from the south drifts northward. A cold air mass is like an invisible mountain of dense air, 3 to 4 miles high and sometimes thousands of miles wide. The air tends to spread out from this high pressure area. But the Coriolis force counteracts this tendency, and the air flowing outward is deflected into a clockwise direction. On a weather map, air masses like this are defined by lines called isobars, which connect points of equal pressure. When the cold air mass encounters warmer air, a weather front is created. Most of the changes in our weather occur at these fronts. The cold air may advance, pushing under the warm air like a wedge. The warm air rises and cools, and its water vapor condenses to form clouds. The result may be rain and a sharp drop in temperature. Forecasting weather depends largely on determining the character and movement of these invisible mountains of air. Mapping centers collect information from weather stations all over the world. Pressure, temperature, and winds are plotted on map segments, which are joined together to form a large map of simultaneous observations. Isobars, the lines connecting points of equal pressure, help the forecaster to locate air masses, fronts, and other important weather features. But a revolution is taking place in forecasting techniques. Electronic computers can analyze data and predict tomorrow's weather map. While machines will soon relieve the forecaster of many routine details, he will still have to interpret air movements and the behavior of warm and cold masses to produce an accurate forecast. But even the most carefully prepared forecasts are frequently upset by baffling and unpredictable developments. Most tornadoes appear so suddenly that they defy prediction. Today, many of nature's elusive phenomena are studied in the laboratory. Looking for clues to the origin of tornadoes, meteorologists photographed a sequence of weather maps. This dynamic presentation of temperature, pressure, and moving air masses over a period of 22 hours describes conditions that may generate unpredictable local storms. Another experiment simulates large-scale wind systems on Earth. A dishpan represents the northern hemisphere. Heating coils warm the water at the rim, much as the atmosphere is warmed in the tropics. A cold source at the center cools the water, as air is cooled at the North Pole. The rotating pan interacts with the warm and cold water and produces currents similar to the wind systems in the lower atmosphere. Thus, the laboratory is helping the scientist to evaluate forces and events too vast to be studied in nature itself. The flow of air is influenced by many factors. For instance, the contours of the land. When winds blow over a mountain range, strong up and down drafts often result. This movement of air is simulated by water flowing across a model of the Sierra Nevada range. By varying the speed of the water, the meteorologist can investigate the mathematical relationship between topography and airflow. The western part of the United States is a classic example of the effect of topography on weather. Moisture-laden air from the North Pacific sweeps across the coast. The coastal ranges force it to rise and cool. Much of the vapor condenses and then precipitates, bringing heavy rains to the western slopes. But once past the mountains, the air descends and is warmed again. It is now very dry, and so are the deserts on the lee side of the mountains. The relationship between topography and weather has become an object of intensive study on the continent of Antarctica. Here, during the International Geophysical Year, scientists of a dozen nations explored the effect of 6 million square miles of ice on weather. Radiation studies showed that up to 95% of the incoming solar energy is reflected back into space by the ice. For this reason, temperatures in the Antarctic are lower than anywhere else in the world, often colder than 100 degrees below zero. Yet observations at Little America have shown that over the past 50 years, there has been a rise in temperature of about 5 degrees Fahrenheit. Findings like these are important to the study of climate, the average weather of a region over a long period of time. We know that climates change. Millions of years ago, parts of Antarctica were semi-tropical. In prehistoric time, the deserts of Africa were lush forests. And as recently as 10,000 years ago, a sheet of ice covered most of the northeastern United States. Many theories have been advanced to explain how these changes in climate occur. Some scientists believe they may be brought about by variations in the energy radiated by the sun. Today, man himself may be changing the climate by releasing into the atmosphere an ever-growing amount of carbon dioxide. We can only speculate on the effect this may have on climate. But suppose the minute carbon dioxide content of the atmosphere were to increase. Suppose, for example, it were to double. This would not greatly affect the amount of solar radiation reaching the Earth, but it would trap more of the heat radiated by the Earth. Average world temperature would tend to rise a few degrees. Glaciers, snowfields, and even the North Polar ice cap might begin to melt. With less ice to serve as a source of cold air, more of the world might well become semi-tropical. We can speculate even further. If there were some rise in temperature, more water would evaporate from the oceans and so increase the amount of vapor in the atmosphere. It is possible, though by no means certain, that more clouds would form. A denser cloud cover would permit less solar radiation to reach the Earth, and average world temperature might drop. Glaciers and ice fields would tend to grow, and another ice age might begin on Earth. But the resulting drop in temperature would eventually remove the cloud cover. More sunlight would reach the Earth. Temperature would tend to go up again, and the cycle might start all over. To increase his limited and entirely theoretical knowledge of climatic changes, and especially to understand our day-to-day weather, the meteorologist continues to study the dynamic atmosphere. A technique that has recently been used in these studies is time-lapse photography, here condensing 6 hours into 1 minute. Time-lapse photography provides the meteorologist with visible clues to phenomena that are difficult to observe. The buildup of clouds, local wind patterns, precipitation, and the development of electrical storms. Today, the scientist explores phenomena in the atmosphere by getting as close to them as possible. He measures electric fields in the air to discover what part they may play in making rain. He uses a wide-angle lens to observe and study great avenues of clouds built by the winds. He even flies into the eyes of hurricanes to find the source of their destructive energy. In their exploration of the atmosphere, meteorologists found they fly clouds, if only under special conditions. When powdered dry ice is sprinkled on some clouds, they may dissolve. This plane flying over Greenland used cloud seeding to clear its own landing path through a heavy overcast. While weather control on a large scale is still beyond man's reach, experiments like these are a first attempt to advance beyond mere observation. Where man cannot go himself, he sends instruments to observe, record, and report in his place. Huge helium-filled balloons carry scientific equipment far beyond the reach of aircraft. Balloons like these have reported new data on solar radiation. They have confirmed the existence of great wind systems some 30 miles above the Earth. The phenomena they observe may have no direct bearing on our weather, but the province of the meteorologist is the entire atmosphere, and all of the elements that form its changing nature. The frontiers of meteorology, like those of the other geophysical sciences, have been greatly expanded by the tools of the space age. Cameras travel hundreds of miles above the Earth to give us a picture of cloud cover over a wide region. From a rocket camera over New Mexico came this composite photograph, revealing hurricane-like storm systems that ground observers could not detect. But the most dramatic and revolutionary results have been obtained from the use of satellites that show man how weather on planet Earth looks from the vantage point of space. Only 7 hours after the launching of Tyros-1, the first satellite equipped specifically as a meteorological observatory, it transmitted back a series of unique photographs showing cloud cover over huge portions of the Earth and indicating that weather systems are far larger than had ever been suspected. Meteorology, once limited to observing local weather, has become a vast and complex science, involving countless technological skills. Today, the meteorologist marshals physics and chemistry, mathematics, and all of the geophysical sciences in his continuing effort to understand the dynamic atmosphere in which we live, our inconstant air.